Good evening, everyone. Our next speaker is an esteemed researcher and variety fields like approximation theory, linear positive operators, who is the popular for being a specialist in the field of approximation theory. He had completed his PhD from IIT Roorkee. It is so impossible to mention his every single accomplishment because they are a lot. He is the author and co-author of 5 books, 15 book chapters, and over 300 research papers. He has often been known to spend hours at scientific meetings for helping students. He is also actively involved in editing several international scientific research journals. Also, he edited several books. With this, I would like to request Professor Gupta to deliver his speech on convergence estimates in theory of approximation.
Good afternoon, everyone. So, is it visible?
Yes, sir. Yes, sir.
Yeah. So, I talk today on some convergence estimates in approximation theory. So,
Hello. Yes, sir. Can you make it full screen, sir? There is an option on the view in the upper menu bar, sir.
uh,
Yes,
which,
sir. Sir, in the upper section, there is a menu bar, sir. File, edit, and view, sir.
okay,
Yes, sir. Just click on that section, and there is a full screen option, sir.
okay.
Yes, sir.
So,
Sir, no, sir. No, sir. In the upper, in the menu bar, sir, where file, edit, and view window helps, sir. In the top left corner, sir. In the view section.
in the view section,
Yes, sir.
okay,
Yes, sir.
zoom,
Yes, sir. In the sir, in the you have seen there's a full screen mode, sir. Control L, sir. In the last third option, sir.
full screen mode.
Yes, sir. Yes,
Yes,
sir. Now it is done, sir. Yes, sir. Thank you, sir.
okay.
It's okay, sir.
So, this is the university where I'm working. This is the main entrance of my university. All thankful the organizers conference for giving me a chance to give a talk, especially Professor Jasovanta Jaina, who worked here and now he is director in Bhubaneswar. Okay, so this is the abstract of my talk. Actually, approximation theory is well-known area in mathematics, and you know it is started by the classical theorem known in real analysis as well as in approximation theory. So this theorem states that every continuous function defined on a closed and bounded approximated by a polynomial function. So there are so many proofs available in the literature of this well-known theorem due to Weierstrass. So some of them are indicated here. The most common proof is based on the Bernstein polynomial, which is given in the year, which was given in the year 1912, long ago. So now we come to the problems in approximation theory. So there, how one can start working in approximation theory. So there may be some direct and inverse results in ordinary and simultaneous approximation. Actually, direct theorems provides the order of approximation for functions of specified smoothness, and inverse theorem is the converse of direct theorems. So it infers the nature of smoothness of function from its order of approximation. One can apply linear and iterative combinations to speed up the convergence. Also, the problem of rate of convergence for functions of bounded variation and for their derivatives of bounded variation. In the year, actually, quantum calculus is not new in mathematics. It is an old area of research in mathematics as well as physics. So we have applied initiated in the year 1997 by Phillips, who considered the Q analog of Bernstein polynomial. After that, when I visited the United States in 2005, myself and my collaborators from Turkey and other places in the world, we have calculus, and we finally we compiled some 30 or 40 completed class. Then we wrote a book on this to calculus. And this was very recently people are working in approximation by difference of two operators. So first of all, we do the extra type operators. Exponential type operators are nothing but these operators can be written just for example ln effect given by this. The kernel k and xt satisfies the partial equation which is given second equation. So there are some operators which are of exponential type, which are Bernstein polynomial. Bernstein polynomial Bnfx is given by Pnkx. Pnkx is the basis of Bernstein polynomial, which is given by k x to the power k 1 minus x raised to the power n minus k. And here x is in the interval 0, 1. As the other operator which is of exponential type is the Baskakov operator. For Baskakov operator, it is based on negative binomial distribution, and it's for this the value of px, which is px function, which is given by, in case of Baskakov operator, is x into 1 plus x. And there are some other Sakian operator based on Poisson distribution, and px is given by x. And its basis as kx is also satisfying the equation of exponential type operators. There are some other operators, one nfx, and here we have different px. So 8,002 years ago, myself, my data around Jain, we have nfx, which is given by here. For this, actually, this was not easy because operators and we got success. Now, second kind for this, we also of this term, and there are some other results. This main result of and so we have of G and rho, the inner, which is given by integration 0 to infinite into t from to infinite k 0 1 to infinite is given by the product. It is closely. Observe that converge to the smile may object. So this approximation results asymptotic may operator with weights of that is not integer functions. So in this case, there are some operators which approximate integer functions. So in this direction, Kantorovich considered first the integral modification of the well-known Bernstein polynomial, where he has replaced p fk by n with this integration k n plus k plus 1 upon n plus 1 ft dt. These operators modified polynomial, which we call as Bernstein-Kantorovich polynomials. These are connected with the Bernstein polynomial Bn by this relation. And for this, similarly, one can define Baskakov-Kantorovich operator, which are connected with the Baskakov operator. But here you see we have Bn. Actually, now we come to some basic concepts what are important in approximation theory. For example, you consider this operator Rnfx, which is the integral modification of the Bernstein polynomial. Here, p and kx is the Bernstein basis function, and integral we are considering in this way. And you see that these are some direct results for this operator in simultaneous approximation. Actually, simultaneous approximation is nothing but approximation of derivative of the function by the corresponding order derivative of the operator. Here I am considering rth order derivative of the operator. So how one can find the better approximation? So there are some operators. For example, Bernstein polynomials, Zaz-Firankian operator, Bhaskakov operators, in which we have these two conditions are applicable. That is, ln E0x is E0 and ln E1x is exactly E1. Ei is just x raised to the power I. But for our operator Rn, this is not exactly x. So one can modify these operators. So myself and my collaborator Oktay Duman from Turkey. This paper is old paper because I am just presenting here my research work which we have done in the last 2 or 3, maybe last 3 decades, and mostly in last 2 decades. So here in the year 2010, myself and Oktay modified these operators Rn, and we considered the modified form of the operator Tn. And for this operator Tn, we observed that Tn1x is 1, Tn(tx) is x, and Tn(t) square is this. But there is some drawback that the original operator was defined in the interval 0, 1, but the modified operator is defined in the interval 0, half. So this is the drawback that we are considering in the compact interval, the new operator. And if we compare our result with the original operator Rn, we conclude that one can get better approximation in the interval 2 by 5, half. Now you come to the conclusion that the original operator Rn was defined in the interval 0, 1. The modified operator Tn is defined in the interval 0, half. But the better approximation can be achieved in the interval 2 by 5, 1 by 2. Although it seems to be very small interval, but there are so many points between this because the original operator is defined in the interval 0, 1. So there are some other methods to have better approximation. So in the year 1976, C.P. May and the R.K.S. Rathore from IIT Kanpur, he considered the linear combinations of some operator, linear positive operators. And for this, they have considered kth linear combination of some, say, operator Dn, which is given by this, Cjkx is given by this, and d0, d1, dk are arbitrary but fixed distinct positive integers. And alternately, we can write these operators in the determinant form, where the first column can be replaced by 1 in the Vandermonde determinant delta. So myself and my supervisor, Professor P.N. Agrawal from IIT Roorkee, we considered the modified form of Bernstein operator Dn, and we considered the kth combination, and we observed that the order of approximation is improved from 1 upon n to 1 upon n raised to the power k plus 1. So by considering the kth combination, we can find that the order of approximation can be improved to 1 upon n, from 1 upon n to 1 upon n raised to the power k plus 1. So this speeds up the convergence if we consider the linear combination. So this is error estimation for our operator when we consider the kth linear combination. So there is another approach to find the to speed up the convergence is the iterative combinations. So which was considered by Michaele for Bernstein polynomials, but we have considered these iterative combinations for some other operators as beta operators, because lot of analysis is involved in finding the analysis. So for this Zas beta operator, if we take the kth iterate, then the operator takes this form. And for this kth iterate, the Zas beta operator, which was given by myself and Govil in 2000, and K. Govil in 2007, and Finta is from Romania, and this is Journal of Mathematical Analysis, and this is old result, and we have considered the Rth iterative, kth iterative combination for Rth derivative. We have also considered the simultaneous approximation here, and we observed that the order of approximation is improved again from 1 upon n to 1 upon n raised to the power k. This is another results in for error estimation. The other result is global approximation. Global approximation means we are considering in the whole interval in which the operator is defined, but here we have to consider the weighted approximation, and which is Jain-Pethe modulus of continuity of second order. So there are some other moduli of continuity. For example, we consider the moduli of continuity of second order, which is given by this multiplied by e raised to the power minus ax, and this is first order moduli of continuity. And for this we consider our next result, which is post reader operator. So this is post reader operator Pnfx, and we want to preserve the xr. So in this case we found a flexibility so that the modified post reader operator is given by this, and here you see that if I put m is equal to r, I get its value to be xr, and but giving different values to m, one can preserve different uh, uh, different monomials. And for this modified form, which preserve the x raised to the power r, we found these results which are flexible. And for this another form is to preserve the exponential function. Here we consider the modified form, also consider the modified form of post reader operator, which preserve e raised to the power ax and e raised to the power bx both. Then the operator takes this form, and for this form we considered these direct results, and this is another direct result. These appeared in some journals, for I don't remember in which journal these papers appeared, and we found we draw the graphs of this by considering the exponential function e raised to the power minus fx's function, which is given by red, and for different values of modified post reader operator we have different lines. And if I increase the value of n, earlier n is 20, and in the next we have consider n to be large, then all graph approaches to one line. So there are some interesting statistics also, Polya distribution, which is well known, that suppose and I don't waste time in this, because this is well known Polya distribution. This is extension of binomial distribution, and you just read it because some people who are working in statistics, they can easily understand what is Polya distribution. So based on this Polya distribution, Stanko in the year 1968 modified the well-known Bernstein polynomial. They have considered actually in Bernstein polynomial you have x raised to the power k. So every time they have an increment in alpha, x plus alpha, x plus 2 alpha, x plus k minus 1 alpha. If I put alpha is equal to 0, then I get x raised to the power k. Similarly here also I take this, and for alpha is equal to 0 we get Bernstein polynomial. For alpha is equal to 1 upon n square in the limiting case, whenever n is infinite we get the Saz-Mirakian operator. And in the year 1987, Alexandru Lupas and Luciana Lupas, they were from Romania. They were very good friends of us, but unfortunately, they both expired in the year 2007. And I wrote some papers with Alexandru Lupas, but he considered the spatial value of alpha is equal to 1 upon n. But it is not spatial, because approximation point of view, one have to consider alpha to be a function of n. Only if I take alpha is equal to 1 upon n, I get the convergence estimates. Otherwise, it will not be possible to find the approximation. So based on the operators of Lupas and Lupas, we considered the modified form of this operator by considering the integral. And actually the moment estimation, which is important in approximation theory, was not easy. So I proposed a problem, although I obtained some moments, first few moments of this operator, but I raised a problem in European Mathematical Society newsletter in I don't remember the year, but a person from Newsport provided its solution in terms of hypergeometric polynomials. And this is the recurrence relation. By using this recurrence relation, one can find the moments of my operator. And these are standard results, direct estimates for this Lupas and Lupas, modified Lupas and Lupas operators. And this is global approximation. Now I come to the another problem, which is Q calculus, which is quantum calculus. Quantum calculus is Q calculus, and it is connected with the H calculus, which is by this relation Q is equal to e raised to the power IH. Actually, quantum calculus is calculus without the limits. So you have 1 plus q square plus q raised to the power k minus 1. If I put q is equal to 1, I get k simply. And it is geometric series. And just like our simple factorial, q factorial can be written in this form. And just like binomial coefficients, q binomial coefficients have this property. And these are simple identities, just like in class 11th, we do some identities on binomial coefficients, but for Q calculus, we have to multiply here by this term. This is simple analysis. And these are some other forms of identities for Q binomial coefficients. And every time we have an increment, suppose I take a minus b q n, it means that a minus b, a minus q b, a minus q square b, and so on. So for example, I consider a minus b square, that this is this, and this is nothing but this. If I put q is equal to 1, I simply get the simple identity, which we know, a minus b whole square. So simple, just like differentiation in Q calculus, we have this form of Q differential operator, which is without limit. So I have given some example also, which is Q integer, which is n. And we have the Q product rule, Q quotient rules for derivatives, Q derivatives. Just like in integration, we have Q integration, but it is not continuous. We have discrete values, which is given by this summation sign. And there are two Q exponential functions, small eq and capital EQ, which are connected by this last identity. And Q beta function of first kind, Q gamma function, and Q beta function of second kind. In case n is integer, then we have this form. Kxn is given by the Kat, you can replace by this, and I have. So based on this, we have first defined the Q analog of Baskerville operator, which appeared in some journals long ago, 10 years ago. So these are weighted approximation for Q Baskerville operator, star-shaped function. These are simple properties. If f is star-shaped, then Q Baskerville operator is also star-shaped. This is the definition of star-shaped function. And Q Durrmeyer operator was introduced by me in 2008. So this is the limiting case of Q Durrmeyer operator. Difference between Q Durrmeyer operator and Q its limiting form. And local approximation we have done, global approximation, and very recently, 3-4 years ago, PQ calculus is further extension of quantum calculus, but there is not much use of this PQ calculus because it is just although it is two-way increment, but when the Q results are available, then one can extend it to PQ easily. So not much use. Some paper appeared in this, but these are simple definitions of myself and Professor Milvanovic in 2018 considered the Q beta function of first kind, PQ beta function of first kind, and for this we have a relation between PQ beta function of first kind and PQ gamma function. And these are also PQ exponential functions. So we actually Michelin in the year 2016. I also told earlier that Michelin considered this to define the PQ Bernstein polynomials, and we considered PQ Durrmeyer operator, and for this some results are available. And very recently we are working in difference of two operators, and for this I considered this, which appeared in RCSM in 2019, and we obtain a general estimate for the difference of two operators, and one can find the quantitative estimations, which we can find, say exact estimations for different operators, Lucas, Kantorovich, Baskakov and Srivastava-Gupta operators in this form. Zaz, Baskakov operator, which we have exact estimates for this. Exact quantitative, you can't say exact because these are quantitative estimates for different operators, because once the general estimate is available, one can. So these are my recent